So the goal for the next, hopefully about 90 minutes, maybe 2 hours, depending upon how fast we go, we're going to go through a bunch of problems. And these come from old exams and practice. They're not the most recent exam, and so you should also look at those problems. Those will probably be gone over in class on Wednesday. Also look at the recent quizzes, including quiz 12, and go to class on Wednesday. It's a review day, and I think it'll be a good review. So, all right, without further ado, here we go. So suppose we have the function f of x, and it's shown below, and we're told that there's this other function, also called f of x, but now with a capital F, and we want to find the integral from, we want to say that capital F is found by doing the integral from 3 minus x up to 2x squared of little f of t dt. So in other words, capital F of x is somehow related to some sort of antiderivative or cumulative function. And we want to determine a couple of things. We want to understand capital F. Now this is a problem where what the goal is to say, let's use the picture and knowledge about integrals to actually find it out. Because we don't have an explicit function, we could probably write one down, but that seems like work, and our goal is let's not try to do too much work. So let's see what A says. We want to find capital F of 1. So we plug 1 into capital F. So according to this, we're going to do the integral from 3 minus 1, which is 2, up to 2 times 1 squared, which is 2, times f of t dt. Now this turns out to be a really easy integral, because whenever your upper and lower bounds match, the answer is 0. All right, because there's basically one way to think about it intuitively, there's no area. Well, that was good. Let's have an example of those types of problems. All right, well, let's try f of negative 1. So what does that say? We're going to plug in negative 1. 3 subtract negative 1. Well, that's 3 plus 1, that makes that 4. We're going to have 2 times negative 1 squared, which is 2, f of t dt. Now notice that these are sort of backwards to how we usually like to go. We usually like to go low number to high number. So we flip. And if you flip the bounds, you change the sign. So negative integral 2 to 4 of f of t dt. Now at this point, we say, okay, we still have to find that integral, but we can interpret it. Because we can think about integration in terms of area. And so in this case, we're going from 2 up to 4. So we can think about it as this shape that we see here. So what is that? Well, it's a triangle. That triangle has area half plus a square, which has area 1. So that's a half plus 1, which is 3 halves. All right. Find f of 0. Well, what will that be? Plug in 0. 3 minus 0 is 3. 2 times 0 squared is 0. F of t dt. So again, we'll flip negative 0 to 3, f of t dt. And now we say, okay, well, what is that? Well, now we go from 0 to 3. So we have that region. And how do you find that? Well, it's half of a circle of radius 1. So here, this is a circle radius 1. So the area of a circle of a whole circle would be pi. Half a circle would be pi halves, plus this little triangle, which is another 1/2. So pi plus 1 over 2. All right. Well, those have been pretty straightforward. But now it's a slightly different type of question where it says, find f prime of negative root 2. So an intermediate step to finding f prime is to say, well, instead of f prime of negative root 2, let's just find f prime of x. So that says to take the derivative. So we come up to the definition. F prime of x is our derivative, integral 3 minus x to 2x squared, f of t dt. All right. Well, now's our first chance to do fundamental theorem of calculus. So let's take 10 seconds, well, probably a little bit more than 10 seconds, to do a quick review, because this is a good thing to know. The derivative, in general, of the integral from some constant to x of f of t dt is f of x. So that's the fundamental theorem of calculus. Now we can spice it up a little bit and start throwing some things in. So for instance, if we want to go derivative of the integral from some constant up to a function h of x of f of t dt, well, what's happening here is we have this h of x function inside of the integral. So it's a function in a function, which means we're going to use the chain rule. So the derivative of the outside would be f, but we plug the inside in, times the derivative of the inside. So this is fundamental theorem of calculus plus chain rule. And the last thing we can do is go all the way and say, well, what if I want a function both downstairs and upstairs? Can we do it? The answer is yes, we can. Because what happens is you can rewrite this expression as the integral from some constant up to h of x of f of t dt plus some g of x up to that same constant of f of t dt. And now switch the order of the bounds, which means you usually subtract. So the moral is this is f of h of x times h prime of x minus f of g of x times g prime of x. So if you see anything where you have an integral and you see functions in your limits, almost certainly there's going to be a fundamental theorem of calculus coming in at some point. You shouldn't be surprised, and you should know how to do it. In particular, if you memorize this, you can do anything. So here we go. What does it say? Well, it says this is f of, plug in the top part, 2x squared times the derivative of the top, which is 4x, minus f of, plug in the bottom part, 3 minus x, times the derivative of the bottom part, which is negative 1. And for right now, that's as far as we really need to simplify. So what do we do next? Well, we're trying to find f prime of minus root 2. So if we plug this in, f prime of minus root 2, that'll be little f of 2 times minus root 2 squared. Well, that's 2 times 2, that's 4. So f of 4 times 4 times minus root 2 minus f of 3 minus root 2, so that's 3 plus root 2 times a minus 1, which makes that into a plus. So now we have to look at the picture and see if we can figure things out. So f of 4, well, that's easy. F of 4 is 1. Then we have 3 plus root 2. Well, root 2 is somewhere between 1 and 2. So this is somewhere between 4 and 5. It's about 4.4, but it doesn't really matter because all numbers between 4 and 5 are the same. This is also 1. So what does that mean? Well, that means we get minus 4 root 2 plus 1. And we're done. All right. So here, testing a couple things. Do the bounds match? Can you switch the order of integration? Can you do fundamental theorem of calculus? And, of course, geometry. We love geometry. There, it's a lot of fun. Find the integral from 0 to 1 of square root of y over y cubed plus 1 dy. All right. So how do you go about doing these problems? There's sort of a simple chart to follow here. So the first thing you should always look at is you can ask, is this one of our basic 8? In other words, one that we should know automatically. There's a list of 8 integrals that you should just look and say, I know how to integrate that. Things like e to the x, x to a power, 1 over x, sine x, cosine x, secant squared, secant x, tangent x, and of course 1 over 1 plus x squared. Now, almost never will be quite that easy. So then the next thing you always say is, okay, is there some manipulation? In other words, can I do some, okay, obviously that was bad planning, but is there some algebra or is there some trig identity that I can do that makes it look like something I can work with? And then the other thing, once you pass that, is to look for substitution. So that's sort of, right now, what you have. Is it one of your basic integrals? Can you do some algebraic manipulation? Or is there a substitution? And that's not too bad. That means we only have a handful of things to try. Now, this particular function is not one of our functions we know how to integrate. So we say, okay, well, it's not that. Is there any manipulation? Well, the answer is no. And I know it's very tempting to look on a test and say, I'm going to come up with new math to help me solve this. For instance, I would wager good money that somebody would say, hey, I have an idea. Why don't I rewrite it and break it up as square root of y over y cubed plus square root of y over 1? Well, there's a reason why you would not do that. And the reason is, this is false. You shouldn't do that. Don't try to be creative. Your algebra hasn't changed just because you're in a stressful situation. In fact, if anything, it's more demanding. So you can break up addition in the numerator, but addition in the denominator, you're kind of out of luck. And there's not really much that we can do here. So we're kind of now saying, okay, there's a substitution to be made. So if there's a substitution to be made, what we have to do is figure out the substitution. Now that comes to the great question, how does one figure out what the substitution is? So recall that the substitution, what you're looking at is you have f of g of x times g prime of x dx. And we're going to do a lot of substitutions because this is sort of the fundamental tool when it comes to doing integration. You're going to do more substitution than probably anything else with integration. So there's two places to look. One place to look is to say, well, can I see the function that's inside of a function? So that's the first place to look. The second place to look is, can I say, do I see something which I recognize as a nice derivative? In other words, is there some part where I say, hey, I know that's the derivative of something I understand? Now in our case, when we look at this, we say, okay, where's a function of function? You could say y cubed plus 1 is inside the function of 1 over something, but it's not so clear that that would work. See, sometimes they're a little bit hidden when you only say, oh, what's the function on the inside? They're a little bit obscured. Is there something that we recognize as a nice derivative? Well, in this case, 1 over y cubed plus 1, no. If it was 1 over y squared plus 1, oh, that'd be good. Oh, that's our favorite. But it's not. It's 1 over y cubed plus 1. But square root of y. So this suggests that maybe square root of y is acting like our g prime of x. So this is what we think might be true. So we say, okay, suppose that's true. What's the antiderivative? Well, square root of y, that's y to the 1/2. So the antiderivative of y to the 1/2, you add 1, that would say that g of y, whoops, yeah, why did I put g of x? G of y. G of y would be something like y to the 3/2 times the constant. All right. Now, technically there's a constant here, it's 2/3. So the constants are easy to manipulate. Don't worry about constants. But now we have a guess. Our guess is this y to the 3/2. All right, so looking for our possible substitution, we said, well, what about y to the 3/2? Then in that case, du, 3/2 y to the 1/2, well, or, said another way, 2/3 du, whoops, I forgot to put my dy here, dy, 2/3 du is square root of y dy. And now we say, well, what does that become to our integral? Well, the square root of y dy becomes a 2/3, which I can pull out, du. And now we have y cubed plus 1. We have to rewrite that in terms of our substitution. Well, y to the 3/2 is not far away from y cubed. In particular, if you take y to the 3/2 and square it, you get y cubed. So this becomes 1 over u squared plus 1. Now we're not done with the substitution because this is a definite integral. So when you're doing definite integral, you need to update the bounds. So the original bounds weren't just 0 and 1. They were y equals 0 to y equals 1. So you need to update those to reflect. So we say, okay, if y equals 0, u is 0 to the 3/2, which is 0. Y equals 1, u is 1 to the 3/2, which is 1. So 2/3 integral 0 to 1 of 1 over u squared plus 1 du. At this point, we should be happy. It's like we've done a substitution. We've made our problem simpler. And we say, okay, time to reset. In other words, I now say, let's think about this integral problem starting from here. So I go back and say, okay, is this one of the 8? Well, yes. This is one of our 8 integrals that we should know. The integral of 1 over u squared plus 1 is arctangent. So 2/3 arctangent of u. Evaluate from 0 to 1. So this becomes 2/3 times arctangent of 1 minus 2/3 arctangent of 0. Well, arctangent of 0 is 0. Arctangent of 1 is pi fourths. 2/3 times pi fourths. We can divide the 2 in. So that's 1/3 times pi halves, giving us a final answer of pi over 6. All right. Well, let's do the next one. Find the average value of f of x, which is x over x squared plus 3, between -2 and 5. So here, there's a key word, or rather a key expression, average value. Now, we should recognize certain things. So whenever we see certain phrases, we're like, aha, I'm going to use that. So average value, in particular, is given by 1 over b minus a integral a to b of f of x dx. That's the formula for average value. So if we see average value, we know right away we're going to pull that out. So that's what we're doing on this problem. All right, so what are we going to have? Well, in our case, this is our a is -2 and b is 5. So our average value is 1 over 5, subtract, -2, integral -2 to 5, x over x squared plus 3 dx. All right, so that's what we have to find. Now, 1 over 5 minus 2 is 1/7. That's not so hard to simplify. Now we think about, okay, how do we do this integral? X over x squared plus 3. So we say, okay, it's not 1 over 8. It's not, there's no really good algebra manipulation to do. So we think substitution. Now, one thing to try here is that x squared plus 3. If you look at x squared plus 3, one of the things to try is say, well, what's the derivative? And the derivative is 2x dx. And we have an x dx. Don't worry about the constants. Constants we can deal with. So this is almost an ideal situation, which says if you let u be the bottom part. So this is a case where we're looking for the inside function, x squared plus 3. du would be 2x dx. Or another way to say this is that 1/2 du is x dx. So that's perfect because we have an x dx. If you ever have a case where you have a fraction and the derivative of the denominator is the numerator, you're perfect. Exactly what you want because you're setting yourself up for a good substitution. So that's 1/7. Oh, why did I put an equal signs there? Integral of, okay, so x squared plus 3 becomes our u. X dx becomes 1/2 du. So we're going to write this as du and put the half out in front because we can do that. And now update the bounds. So the old bounds were x. So to get u bounds, we plug it in. -2 squared is 4. Plus 3 makes 7. 5 squared, 25. Plus 3 makes 28. So now we have this integral. And we say, is this an integral we can do? And the answer is, yes, we can. 1 over u. It's on our list of 8. 8 integrals that we should know. So this is log of u. We have a 1/14 in front from our constants, and we're going to evaluate from 7 to 28. So we're going to have 1/14 log of 28 minus 1/14 log of 7. Now, one thing you can do here is you can use properties of logs. Logs are really nice functions, and we get a lot out of them. So in particular, you can think of this as 1/14 log of 28 minus 7. And it's important to know properties of logs and to use them correctly. So if we have subtraction, well, subtraction becomes, do you remember? Division. Yes, 1/14 log of 28/7, or 1/14 log 4. So that's pretty simplified. You can do a few other things, but that looks pretty nice. It's pretty condensed. All right, that's not so bad. Find the following. Integral sine x, cosine x, square root of 3 minus cosine x dx. Now we get back through our process. We start saying, okay, what are things we can do? It's not on our list. There's not any obvious manipulations. I mean, there are things you can do, but the goal of any problem when you're doing integration is to say, can you simplify it? And there's oftentimes lots of things you can do to complicate things, but you don't want that. You want to simplify things. All right, so we're sort of leading towards saying, we've got to do substitution. All right, what should we substitute? What stands out? Any suggestions? Well, here I see a 3 minus cosine x inside a square root. So this is a function in a function, and that's oftentimes a good place to start looking. So let's see where that would take us. Suppose we set u equal to 3 minus cosine x. And let's follow that down. Well, so if u is 3 minus cosine x, what would du be? Well, derivative of 3 is 0. Derivative of cosine is negative sine. Minus minus makes positive sine x. And then we say, aha, good news. We have a sine x dx. That will become our du. But now, there's one piece of like, is this going to work? We have that also sitting there, cosine x. Because we have to update everything. We can't just say, I'm going to update part of it and leave part of it alone. You have to update everything when you're doing substitution. So here's a case where you say, hey, I know what to do. This u equals 3 minus cosine x, I can actually solve it and say that cosine of x is 3 minus u. So that this part can become 3 minus u. So if you do that substitution, we're going to have the following. Sine x dx becomes du. Cosine x, 3 minus u. And square root of 3 minus cosine x becomes square root of u. Now, because we're doing calculus, we don't use the square root symbol. We use u to the 1/2 because our calculus rules are built for u to the half. So I'm going to multiply that through. This is our algebra manipulation. In other words, distribute that square root of u. That's 3u to the 1/2 minus u to the 3/2 du. And now we're in good shape. So if we integrate that, well, add 1 to the exponent. That'll be u to the 3/2. And then I'm going to multiply by the reciprocal, 2/3. Minus, here I'd add 1, I'd get u to the 5/2, multiplied by the reciprocal 2/5. And always remember plus c. If you're dealing with an indefinite integral, you better put plus c. And if you don't, you're going to lose a point. And you don't want to lose a point. You want to get them all. Okay. Now, there's a little simplification. The 3's cancel. Are we done? No. Hasn't been circled yet. There must be something remaining. Well, the remaining thing is to say, we got to go back to where we start. Because this is an indefinite integral. So whatever you started with, in this case we started with x, you have to end with x. On definite integrals, you always go forward. You never have to go back. So this becomes 2. And replace u by 3 minus cosine x to the 3/2 power minus 2/5. And then 3 minus cosine x to the 5/2 power and plus c. And that's it. And we're done. All right. Good. Find the derivative of t cubed e to the t cosine of x squared dx. Now this relates to what we were talking about before. In other words, it's another one of these fundamental theorem of calculus problems. So in some sense, this should be pretty straightforward. We say to ourselves, well, is there anything that's a little different that might throw us off? And there is one small thing, but I want to point out that this shouldn't throw us off. Namely, here, x's are acting as the variable on the inside, where it's the t's are the variables that we're actually working with. So they sort of swapped roles. So in other words, the x's and t's changed their roles. Does that change anything? And the answer is no. No, it still works the same way. So this is a question that says, do you know how to apply the fundamental theorem of calculus? And the answer is, of course we do, because it's fundamental. So it's important. And it even has the word fun at the beginning, which means it's a really good thing to do. Okay, so the rule says to take this derivative, you take your function e to the t, and you plug in wherever you see your x. So in this case, it would be cosine of e to the t squared. So instead of x squared, it's e to the t squared. Then you times that by the derivative of e to the t, which is e to the t. Subtract cosine, and now you're going to plug t cubed in wherever you see an x. So it'll be t cubed squared times the derivative of t cubed, which is 3t squared. And unless we're told otherwise, we're done. Oftentimes, we don't need to simplify. In some sense, it's better not to simplify because, well, two things can happen. One, we make a mistake and we lose a point. It has happened where people have correct answers and then they're just like, I want to simplify, and then they get incorrect answers. That's not fun. The other danger, of course, is when it comes to grading. If you do make a mistake, if you don't simplify, it's easier for us to figure out what kind of mistake and give more partial credit. Consider the following table, which gives information about the function f of x at some points. I won't read the table, but there it is. Use this information to approximate the area under the curve y equals x f of 2x from x equals 0 to x equals 3 using Riemann sums with 6 equally sized parts and using the right endpoint in each part. So this is a question about Riemann sums. So Riemann sums, the idea is we're going to break things up. Now really when we talk about breaking things up, what are we breaking up? We're breaking up our input. So x equals 0 to x equals 3. So I'm going to go from 0 to 3. And what am I doing? Well, I'm going to break this into 6 equal parts. Okay, I'll start by breaking into 3 equal parts and then break those up into equal parts. So there's 6 equal parts. Now, once you know it's 6 equal parts, it's not hard to figure out what the widths are. Because you're going from 0 to 3, and so that's a length 3. Divide 3 by 6 is a half, which means that we're going up in step sizes of a half. So we have a half, 1, 3 halves, 2, 5 halves, 3. So those are our points. So those are the intervals. All right. Now, what's happening? Well, we're going to use the right endpoint in each part. So in other words, for each interval, we're always going to be biased towards the right-hand side. So in particular, we should, if we're doing 6 intervals, we should have 6 parts. All right. Now we're almost there. So what's a Riemann sum? A Riemann sum says, in general, we're going to take the sum of our function at our points times the widths of the intervals. So we should understand the widths. Well, the widths, because we're equal, all our widths are going to be a half. So we're pretty much rounding the corner. So let's let, for just convenience, temporary convenience, g of x be equal to x f of 2x. Now our answer is going to be the following. We're going to apply g at a half, figure what that is, times a half, plus g at 1 times a half, plus g at 3 halves times a half, plus g at 2 times a half, plus g at 5 halves times a half, plus g of 3 times a half. All right. Well, it takes longer to write it down than to actually figure out what's going on. Everything has a half, so you can actually factor that out. And then we say, okay, so what do we do? Well, we're going to take x times f of 2x. So when I plug in a half, that's really 1 half f at 1. Plus, plug in 1, that'll be 1 times f of 2. And then 3 halves f of 3. And then it'll be 2 f of 4. Then 5 halves f of 5. And finally 3 f of 6. So we're going to have a half. That's our widths. Now we plug in the table. So we come into 1. Okay, so here's 1. So that's going to be a half times 0.8 plus 1 times, plug in 2, 0.6 plus 3 halves times whatever happens at 3, which is 1.2, plus 2 times what happens at 4, which is 1.6, plus 5 halves times what happens at 5, which is 2.0, plus 3 times whatever happens at 6, which is 1.8. And we could actually stop here. There's no reason, unless it says to simplify. Well, out of curiosity. Okay, 1/2. So half of 0.8 is 0.4 plus 0.6. 3/2, well, 1.2 divided by 2 is 0.6. So that's 1.8. 2 times 1.6, that would be 3.2. 2 into 2 gives 1 times 5 is 5.0. And 3 times 1.8 is 5.4. And you add these up, 10.4, 13.6. Probably shouldn't have added them up. 13.6 plus 1 is 15.4. 16.4 times 1/2 is 8.2. Okay. You probably could have stopped there, unless it said to simplify. So Riemann sums, there's sort of 3 flavors of Riemann sums, and we're probably going to see 1 or 2 more Riemann sum problems. Either they're going to give you an explicit function, and you use the function. They're going to give you a table, then you use the table. Or they're going to give you some other way to convey information about a function. So they might give you some graph, and they say, oh, okay, what's happening to this graph? And in that case, you don't know what the function is, but you say, look, I can see where it crosses certain points. Essentially, it's just another way to give you a table. But they're all more or less the same. It's like, okay, break it up. Figure out how do you break up your interval, that's your input. Where are the right endpoints that you use, or where are the correct points that you use? And add them up. So they're not too bad. People do pretty well in Riemann sum problems. Find the area between the curves y equals 2x squared minus x sine squared x plus 1 and y equals x squared plus x cosine squared x plus 3. So we have 2 curves. We don't know quite what they look like, and we suspect they might have a little bit of wiggle in them because they have these sines and cosines inside. So areas between curves, well, how do we go about that? Well, in general, what we think of is we have some function on the top and we have some function on the bottom. So let's say g of x is our top function and f of x is our bottom function. To find the area, we figure out where do they intersect, and then we integrate a to b, the top minus the bottom. Now, that's not so bad if you know what a and b. And sometimes they say, here's a and b, but sometimes they don't. So what if they don't? Well, if they don't, you have to find where they intersect, which means you set the curves equal. So 2x squared minus x sine squared x plus 1 would have to equal x squared plus x cosine squared x plus 3. And this is looking a little bit, we're getting nervous, because whenever you see trig and algebra mix, they tend not to mix very well. Well, we have to do something. Okay, move everything across, and what do you get? 2x squared subtract x squared, that's x squared, minus x, and I'll go ahead and factor, there's an x, sine squared x, and there's also a cosine squared x, that was times by minus x, and plus 1 minus 3 is minus 2. Sine squared plus cosine squared is 1. Ah, good. So really, these intersect when x squared minus x minus 2 equals 0. Well, hopefully by this time you've come to the belief, unreasonable though it is, that everything factors. In this case, it does. X minus 2 times x plus 1 equals 0. So x is negative 1 and 2. So those are our points of intersection. That's where the curves are going to cross. Now, there's still one question to ask, is which curve's on top? And the way to figure that out is to say, okay, we'll just pick a point somewhere in the middle. So what's somewhere between negative 1 and 2? Anyone have a favorite number between negative 1 and 2? Yeah, 0 is a great choice. Plug in 0, you get 0, 0, 1. Plug in here, 0, 0, 3. So that means that this second curve is the top curve, and this first curve, that's the bottom curve, because it's smaller at 0. So we're almost there. So now we know how to set it up. It's the integral from negative 1 to 2 of the top, x squared plus x cosine squared x plus 3, subtract the bottom, 2x squared minus x sine squared x plus 1. All right. Now, when you do this, you're going to see something familiar pop up. So the x squared minus 2x squared becomes minus x squared. then you're going to get the x cosine squared minus becomes x sine squared, which is going to become plus x. And then 3 minus 1 is plus 2. Now, the reason I say you might see something familiar pop up is if you look at that, this part looks an awful lot like that part. That's not a coincidence, because when we were finding the intersection, we were really finding when are they equal, which means the differences. So it's not a coincidence that they were the same. In fact, if they weren't the same, we'd be nervous because we'd made a mistake. All right, so what does this become? Well, integrate minus 1/3 x cubed plus a half x squared plus 2x. Evaluate from -1 to 2. So that's minus 1/3 times 2 cubed, so I'll write that as minus 8/3, plus 1/2 times 2 squared, which is 2, plus 2 times 2, which is 4. Going to subtract. Minus 1/3 times minus 1 cubed, so that's going to become a minus 1 again, so that's minus makes plus 1/3. So minus 1/3 times minus 1, then plus 1/2 and minus 2. So we get minus 8/3 minus 1/3. Well, that's minus 9/3, which is negative 3. Plus 2 plus 4 plus another 2. So that's plus 8 more, minus 1/2. That's 5 minus 1/2, which would be 9/2. All right. So there you go. Okay, that's not so bad. In general, you should expect things to work out nicely. If your problem is getting very complicated, you should be suspicious. A lot of the problems are set up so that if you follow the correct process, everything works out pretty well. Should not get too much crazy algebra. All right, find the integral 0 to 8 of dx over 1 plus the cubed root of x. Well, that's different. All right. Well, any suggestions? Substitution? Yeah, that seems to be the best thing to do. Definitely it's not on our list of things we can integrate. There's no good algebra that we could do that would make it a lot better. So substitution. So substitution, there are sort of two things to try. You could say, well, what if I just try just cubed root of x? Well, that would be okay. You'd end up with a 1 plus u downstairs. So in this case, I think it's better make the whole thing the substitution. So we're going to put the whole denominator. U is 1 plus the cubed root of x. All right. Now, we should be slightly nervous, because if you look at it, that's pretty much, we said everything is u, which means almost nothing is left to handle the du. Well, we're good. We can figure this out. All right, let's see what follows. So u is 1 plus cubed root of x, which for convenience we write as x to the 1/3. So we take the derivative, du. So that will be 1/3 x to the minus 2/3 dx. And now we come to our moment and we start to panic ever so slightly. Have we made a series of bad life choices that have led us to this moment that says that we're not going to be able to make progress? Or is there still hope? Well, I'd like to think there's still hope. All right, what do? There's not an x to the minus 2/3. So what we can do is we can say, well, if I could move this around, let's move it across. The dx is going to end up being 3 times x to the 2/3 du. Now my problem is I have to get everything in terms of u. So I can't have a little leftover remnant of x. So now I say, okay, can I do something to x to the 2/3? Well, x to the 2/3 is secretly x to the 1/3 quantity squared. And the reason I point this out is I know something about x to the 1/3. In particular, I know that x to the 1/3 is u minus 1. So I can say dx becomes 3 times u minus 1 squared du. Now we're in good shape, because what's going to happen? We're going to do an integral. The dx is going to become 3 u minus 1 quantity squared du. The 1 plus q derivative of x is going to become u. So we can get everything now in terms of our new variable. This is a definite integral, which means we need to update our bounds as we go. So our old bound was 0. So to get our new bound, we plug in x equals 0. The q root of 0 is 0, plus 1 makes 1. Plug in 8. Q root of 8 is 2, plus 1 makes, q root of 8 is 2 plus 1 makes 3. Okay, that's fine. All right. So what's next? What's our next thing we do? What? Well, we don't have to go in terms of x. We have everything in terms of u. How do we integrate this? So now, ignore where the problem came from. Suppose this was your first problem that you saw. Because when you're doing substitution, you move forward. Okay, what would we do? Well, is this one of our 8 things we can integrate? Not yet. Is there any algebra we can do? We can expand. So this is a case of use your algebra. 1 to 3, 3, u squared minus 2u plus 1 over u. But we can even keep going, because when I see addition and subtraction upstairs, that says I can do it over each term individually. So I can think of this in the following way. 1 to 3, u squared over u will be u. Minus 2u over u will be minus 2. Then there's a 3, so that's minus 6. And 1 over u is 1 over u. Now whenever you have things being added and subtracted, we say, can we integrate each part? And I think we can. The integral of 3u, well, that's u to a power. You add 1, u squared, divided by the power 2. Integral of negative 6, negative 6u. Integral of 1 over u, that's on our list. That's the log of u. And we're going to evaluate from 1 to 3. So, let's see what we get. When we plug in 3, we're going to get 27 halves minus 18 plus 3 log of 3. And from that, we're going to subtract 3 halves minus 6 plus 3 log of 1. Well, we can cancel, maybe not cancel, but at least knock out. 3 log of 1 is 0, so that term is gone. 27 halves subtract 3 halves would be 24 halves, which would be 12. Then I have minus 6 is plus 6. Then I have this minus 18 plus 3 log 3. Well, 12 plus 6 minus 18, that's going to knock out. That's all gone. So, what's left? 3 natural log of 3. And that's the answer. It comes out pretty nice. All right. Good. Well, let's do another one. The integral of 1/2 to 1 of r of x. We want to find that. And we're not told what r of x is, but we're told a lot of information. The integral from 1 to 3, r of 2x dx is 5. Integral from 1 to 2, r of 3x dx is 4. Integral from 4 to 3 of r of x dx is 2. And integral from 0 to 1, r of 5x dx is equal to 6. Now, how do we go about using this information? Well, somehow we want to make things more compatible. So let's try to get everything in terms of just r of x. So I want to write everything in terms of r of x. So this one is good. We're happy with this one. The only thing is, let's change the bounds. So we can say here, the integral from 3 to 4 of r of x dx is negative 2. Because if I swap the bounds, I change the sign of the answer. All right, let's look at all of these one at a time. Here I'm going r of 5x. So I'm going to say u equals 5x. Then if I do that, we'll get du is 5 dx, or dx is 1/5 du, which means that this will become the integral. I multiply my bounds by 5, so 0 up to 5 of r of u times 1/5 du, which is 6, or integral 0 to 5 of r of u du is equal to 30. Okay, we should probably switch this to have u as well. So 3 to 4 r of u du is negative 2. This is using the famous substitution x equals u, which just says, just change the name. It's all about changing names, really, at the end of the day. All right, well, how about this one? Similar process. U is 3x, du is 3 dx, or dx is 1/3 du. So this would become the integral. So multiply my bounds by 3. 3 to 6, r of u, 1/3 du equals 4. So integral 3 to 6 of r of u du is 12. All right, and then the first one, well, u equals 2x, du is 2 dx, or dx is a half du. And so we get the integral 2 to 6 of r of u, a half du is 5. So the integral from 2 to 6 of r of u du is 10. So we have all that information. Now, that's what we have. We do the same thing with what we're after. So let's let u equal 4x. Du is 4 dx. Then this integral here becomes what? Well, becomes 1/4, which is going to come from that 4. Integral 2 to 4 of r of u du. So we are trying to get 2 to 4. That's our goal. If I can go find a way to get the integral from 2 to 4, life is good. Well, how do we do it? We start in saying, well, where's the 2? The answer is, there's a 2 right there. So I'm going to start there. So I have the integral 2 to 6 of r of u du. Next up, I say, okay, does anything have a 6? Well, this has a 6. So what I'm going to do temporarily, and I'll come back and change this in a second, is I'm going to go 6 to 3. Now, why do I want to do this? I really want these bounds to match. Because if those bounds match, 2 to 6, 6 to 3, it's the same as 2 to 3. All right, now what? Well, I say, does anything have a 3? And, well, there is something that has a 3 right there. So I'm going to add integral 3 to 4 of r of u du. And now, why do I like this? Because these bounds match. So 2 to 6, 6 to 3, 3 to 4 is the same as 2 to 4. So this is equal to the integral from 2 to 4 of r of u du, which is really what we're after. Now, integral from 2 to 6 is 10. Integral 6 to 3 is the opposite, because I have to change the order. So that's minus 12. And integral from 3 to 4 is minus 2. So I have 10 minus 12 minus 2. So that'll make this integral equal to negative 4. So is that our final answer? Well, almost. We showed that was negative 4. So we're going to get 1/4 times negative 4, which gives us the final answer of negative 1. All right. So this is about manipulation, and really it's about substitution. Do you understand substitution? Do you understand how to make the bounds match? If your bounds match, you can glue things together. So this is testing a couple of different concepts. All right. So for time, we usually think of when we see t as time. Between 0 and pi force, a particle has a of t, and that stands for acceleration, 2 secant squared t tangent t. Given that at time t equals 0, the particle is located at position 2 and has velocity 3, determine the particle's speed and velocity at time t equals pi force. So this is motion. So we're going to try to understand motion. So there's motion, we have 3 aspects. We have acceleration, which we'll write as a of t, and this is something we already know. 2 secant squared t tangent t. Then we have velocity, which we don't know. And then we have position, which we also don't know. But we're going to figure those out. And the way we think about this is we say, okay, how are things related? So, for instance, how are acceleration and velocity related to one another? What's the answer? Well, so we talked in the first part of the course, if I start with position, I can take derivatives to move up. So the second part of the course, we're going backwards. If I have acceleration, I can get to position by taking the opposite of derivatives, or if you like, the anti-derivatives. So now we're really about anti-derivatives. So let's figure out velocity. So velocity is the antiderivative of acceleration. So I need to integrate 2 secant squared t tangent t dt. So now we started saying, okay, how do we integrate 2 secant squared t tangent t? So we think about our list of things that we know the integrals of. And our goal is always to say, can I make things look like things on that list? Now this involves secants and tangents. And so if we go back to our list of things we know how to integrate and things we know how to differentiate, one of the things that we have is that we have the integral of secant squared t is tangent t, and then there's a plus c, and the integral of secant t tangent t is secant, and then again a plus c. So those are sort of the things that we would be thinking of looking at. So in particular, we want to say, can we use those facts? Unfortunately, that square there does not match up with the current expression. So I can't say, oh, this is one of my 8, because it's not one of my 8 things yet. So since it's not one of the 8 things, we have to say, okay, it's not one of those. We are tempted to think trig identities, but trig identities can be very dangerous because there's too many of them. So we oftentimes want to use trig identities very carefully and with purpose. And right now, I don't have a purpose yet. So I'd like to look at substitution and ask, is there a good substitution to make? So, in particular, when I'm thinking substitution, I think of sort of the opposite. See, I think of, what's the derivative of tangent? Well, the derivative of tangent is secant squared. What's the derivative of secant squared, or secant? Well, secant tangent. And now, I'm actually kind of happy with either one of these because I see both the secant squared and I also see a secant tangent. So it says there's choices to make. Does anyone have a preferred choice? You know, it's okay. You don't have to have a preferred choice. I'll go with secant tangent. Okay, so what am I saying here? Well, what I'm saying here is that secant tangent's a good derivative. So, if I think of it in the following way, 2 secant t times the secant t tangent t, what's happening is we're setting this up so that this part right here is acting like our g prime, and this part is acting like our f of g. So, the substitution in particular, if we use this format, and again there's actually 2 choices here, which is fun. There's more than one way to do stuff. Oh, that's so cool. So we're going to let our substitution be our secant function. Then our du will be secant t tangent t dt. And our integral becomes 2 secant, which becomes 2u. Secant t tangent t dt becomes du. Well, the integral of 2u is u squared. And of course, tack on a plus c, so this becomes secant squared plus c. All right. Now, have we found velocity? Kind of. What don't we know? We found velocity up to a constant. So we have velocity almost. The part we don't know is the plus c. So now we have to scour and say, is there any information? So we're looking about information about our velocity, and we're told the following, that at time 0, there's velocity 3. So that's information we use to figure out what the right constant is. So velocity at time 0, we plug it in, Secant of 0, do we know secant of 0? It's 1. Secant of 0 is 1 plus c, but that's also supposed to be equal to 3, which says c is 2. And therefore, velocity is secant squared of t plus 2. All right. So there's our velocity. Now, we also want position. Speed and velocity. Whoops. That's supposed to be position and velocity. Speed and velocity are almost the same thing. All right, we're going to find position and velocity. We could argue that we're done now, but I want to go more. Okay, position. All right, how do you get position? Take the integral of velocity, which, let's hope we can fit it in here. So s of t, it's the integral of secant squared t plus 2 dt. Now, are these things on our list? Yeah. See, oh, this is great. We don't even have to work hard for the second layer. Integral of secant squared, tangent. Integral of 2, 2t, or not to t. That is the question. No, wait, no, it's 2t. Plus, again, another constant. And here, we use that information. So at time 0, our position is 2. So position at time 0, tangent of 0 is 0. 2 times 0 is 0, which means we have d, which is 2. So that turns out we know what d is. So our position is tangent of t plus 2t plus 2. Now, we're ready to answer the position and velocity at pi force. So, our final answer is going to go in here. Our position is, plug in pi, why did I plug in 0? Our position at pi force. Tangent of pi force, 1. This is plus 2 makes 3. 2 times pi force is pi halves. 3 plus pi halves. Our velocity at pi force, well, secant of pi force, do you know that one? It's square root of 2. Square root of 2 squared is 2, plus another 2 makes 4. And there's our answer, our position and our velocity. Now in this case, we didn't give units. We could have given units. We could have said that our position is meters, our time is seconds, and in that case we'd throw units on. If it says include units, include the units, because that's the point. And we want to make sure we get all our points, because we want to get them all. Got to get them all. Okay. Well, let's try another one. For x greater than 0, find f of x, given that we have this expression. The integral from x to 2 of tf of t dx is e to the 3x minus x plus some constant times cosine of pi x plus 2x plus 1. So I have to figure out what is the right expression for f of x. Now, we also have this strange thing here, which is that there's a constant that's not given. So let's try to tackle the question first of what that constant should be. So I want to find that constant. How can we find that constant? Well, let's look at our expression and ask ourselves the question, is there a value for x where we know that integral? And which x is it? The answer is there is a value of x where we know that integral. It's at 2. See, there's a nice fact that says if I ever have the bounds match, the integral is 0. So let's look at x equals 2. What we get is that the integral from 2 to 2 of tf of t dt, well, that's 0. So that's going to be equal to e to the 6 minus 6, which is e to the 0, which is 1, plus c times cosine of 2 pi. Well, cosine of 2 pi is the same as cosine of 0. It's 1, so that's plus c, plus 2 times 2, which is 4, plus 1. So once we plug in x equals 2, we come to the conclusion that we better have c is equal to -6. Okay, so that's a little bit better. Integral of x to 2 of t f of t dt is e to the 3x minus 6 cosine of pi x plus 2x plus 1. Now, we want to somehow get to just f. How can we do it? Well, this reminds us of saying, okay, I want to get rid of this integral, because the f is currently inside the integral. So what's something we can do to get rid of that integral? Well, we could apply a derivative. So if you take a derivative of an integral, you get back what's on the inside. So we want to get that f from outside, we want to free it from that integral. So we're going to use a derivative to do that. Probably it's also useful to get the order from 2 to x. So let's do that really quick. 2 to x of t f of t dt. If I swap the bounds, what happens? I change the signs. Minus e to the 3x minus 6 plus 6 cosine pi x minus 2x minus 1. And now we do our fundamental theorem of calculus. Okay, so apply the fundamental theorem of calculus, which means we take the derivative of both sides. What's the derivative of the integral from 2 to x of t f of t dt? Well, the answer is you take this x and you plug it in for t. So that's x times f of x. The constant down here means that there's no second part. Well, so that's the derivative of the left-hand side. What's the derivative of the right-hand side? So we go through term by term. Derivative of minus e to the 3x minus 6, that's minus 3 e to the 3x minus 6. Derivative of 6 cosine pi x will be minus, the derivative of cosine is negative sine, and then we have to remember to include a pi here. So minus 6 pi sine pi x. Derivative of minus 2x is minus 2, and the derivative of minus 1 is 0. So that's what we get when we take a derivative. All right. And so we're almost there. So that's x f of x is equal to that. So finally, to get f of x, divide everything by x. So minus 3 e to the 3x minus 6 minus 6 pi sine of pi x minus 2 all over x. And there we go. We have our function. So pretty much any time you see an integral and you see a function in one of your bounds, there's a good chance fundamental theorem of calculus is going to come in. And that's exactly what the fundamental theorem of calculus was built to do. All right, approximate the area under the curve y equals 4x squared minus 2x from x equals 1 to x equals 5 using a Riemann sum with the interval split into 4 equally sized parts and using the central point in each part. So here, this is a Riemann sum problem where they give us the function. So that's good. We just need to understand where we're going to evaluate. So we're going from 1 to 5. Now it turns out that the distance between 1 and 5, we take 5, subtract 1, that's 4. So the spacing here is 4. We want 4 equal parts, which means what we want to do is we want to make it so the parts all have width 1. So 4 over 4 is 1. So that means that our 4 equal parts are going to be 1 to 2, 2 to 3, 3 to 4, 4 to 5. Now, those are our intervals. And one thing that's important to note is that all the widths here are 1. Okay, well that's a part of the expression. So these are our delta k's. There's always 1. Now we need to know where we're evaluating, because for each interval we have to pick a point. Because it depends. We have a lot of freedom, and oftentimes we're told which point to pick. A left point, a right point, a middle point, or maybe where's the function large or where's the function small. So in this case we're told the central point. What's halfway between 1 and 2? 1.5, also known as 3 halves. Halfway between 2 and 3? 2.5, also known as 5 halves. Between 3 and 4? 7 halves. Between 4 and 5? 9/2. So, our answer, well, our Riemann sum is the sum of f, xk, delta k. In our case, because our delta k is 1, then this will be just the function evaluated at the right points. So f of 3 halves plus f of 5 halves plus f of 7 halves plus f of 9 halves. So now we just go through and evaluate. So this is our f. So we're going to get 4 times 3 halves squared, which is 9/4, minus 2 times 3 halves, plus 4 times 5 halves squared, that's 25/4, minus 2 times 5 halves. And I should have started further to the left because I'm going to run out of space. 4 times 7 squared is 49/4, minus 2 times 7 halves, plus 4 times 81/4, minus 2 times 9 halves. So if I start over here, so I have plenty of space, that becomes 9 minus 3 plus 25. But why did I put minus 3? I said 9 minus 3. I just put 9 minus 3, 25 minus 5. Double check. It's easy to make mistakes in copying. 49 minus 7 and 81 minus 9. And you can add these up. 9 plus 25, that's 34. 49 plus 81, that would be 130, plus 34 makes 164. And let's see, we're going to subtract 3 and 5 makes subtract 8, then minus 7, subtract 15, subtract 9 more, subtract 24. 165, subtract 24 is 141. All right. Again, if your problem doesn't require you, you probably should stop. If it doesn't say simplify as far as possible, just get to a point where you have an answer and say, this is the right answer, and I'm happy leaving it as is. Okay. Rewrite the following as a single integral. In other words, just one integral to rule them all. One integral to find them. Okay. So what are we testing on here? Well, we're testing on some key ideas and saying, okay, well, let's figure out what happens. So I want to have everything in terms of a function of u du. So we're going to probably do some substitution. So in this case, the substitutions are pretty clear to follow. So e to the x, that would be u. Then du would be e to the x dx. So that's good. So if we make the substitution here, u equals e to the x, then we get du is e to the x dx. This would become integral, and we got to update the bounds, so always remember to update the bounds, because these are x bounds. X equals 0 to x equals log 3. We want u bounds. So e to the 0 becomes 1. E to the log 3 becomes 3. And now we have e to the x dx becomes du, and then f of e to the x becomes f of the function u. So that's what the first integral becomes. Okay, so that's the first one. Let's do the second integral. So on the second integral, well, we're pretty much told what to do, because I need to have function of u. So there's our u is sine of pi x. Well, du will become pi cosine pi x. And now I start saying I'm in trouble, because I don't have a cosine pi x. I have sine of 2 pi x. So here's a case where a little bit of trig knowledge is a good thing to have. So what's another way to write sine of 2 pi x? Well, anyone know? this case, there's a nice fact called double angle identity. Sine of double an angle is 2 sine of the angle cosine of the angle. So sine of 2 pi x, I can think of this as doubling the angle pi x. Because notice that's what I have here is a pi x. So I've doubled that angle. So this can become 2 sine of pi x cosine pi x. And now I have a cosine pi x. All right, so let's see. What do we have? Well, we're going to have a lot of stuff. Okay, let me move that 1 over pi across. So we're going to have the integral. We have that 2 there. We have a 1 over pi. Cosine pi x dx. Well, we'll grab those terms. So that now we have our du. F of sine pi x becomes f of u. But we still haven't accounted for our sine of pi x. So that means that's going to become a u. So that's what we're going to get. 2 over pi integral of u, f of u, du. Now this makes us a little nervous because we don't want a u, f of u. We want just f of u. Well, there's something else we haven't done though. What haven't we done yet? We haven't done the bounds. So let's do our bounds. Plug in x equals 3. Sine of 3 pi. Sine of 3 pi, also known as 0. Plug in x equals 6. Sine of 6 pi, also known as 0. What's that integral going to become? 0, which means this middle part goes away. So it's okay that it looks terrible because it's just a bad way of writing 0. Or maybe it's a great way of writing 0. It just depends on your perspective. All right, rounding the corner. 8 minus a half x. That'll become our u. Du is minus 1/2 dx. Well, so minus 2 du is dx. So what do we get? Well, integral, the 1/2 is there. Minus 2, that's there. Then, so I pull out the half. I have the minus 2. So that takes care. We have our du and our function of u. What's left for us to do? The bounds. So we plug in our bounds. When we plug in 6, what do we have? Well, 8 minus a half times 6. Well, that's 8 minus 3, which is 5. Plug in 10. 8 minus 1/2 times 10. That's 8 minus 5, which is 3. Now there's something we can do here. Well, there's probably several things we can do here. One easy thing is we can knock out the 2's. Also, we see that our bounds are sort of backwards from how we usually like to write them. But we also have a minus. So that's great. We can actually fix that. We'll put our bounds in the right order, 3 to 5, and then just drop the minus because that'll go away. So, what do we have? Well, we're left with the integral from 1 to 3 from the first term. Our second term dropped out, and the integral from 3 to 5 of our last term. Now, we want to get a single integral. So we want to combine these two, but we're in luck because they match. Meaning that we can combine these nicely. So the 1 to 3, 3 to 5 is 1 to 5. And there's our answer. All right. Find the integral of sine theta over cosine squared theta plus 1 minus sine 2 theta over cosine squared theta plus 1. All right. Well, how much difference can a 2 make? The answer is, it might surprise you. It makes a lot of difference. Now, one of the things that you should think of is if I have subtraction or addition, I can really think of these as two integrals. So let's break this up into two problems and see what happens on each problem. So I have the integral of sine theta over cosine squared theta plus 1 minus the integral of sine 2 theta over cosine squared theta plus 1. We just a few moments ago talked about sine 2 theta. So this is a case when it's a good idea to apply your double angle identity. So sine of 2 theta becomes 2 sine theta cosine theta. Now, you might say, but how do you know to do that? The answer is we really, whenever we have trig involved, we want them to be compatible in what's on the inside. So in other words, if you look at the theta and the 2 theta, they really don't match. One of them's a theta, one of them's a 2 theta. I want them to match. So I'd like everything to be just theta, or I'd like everything to be 2 theta. And in this case, it's easier to have everything in terms of theta. All right. So now comes our time when we start and go, what can we do? What can we do? So again, think of these as 2 integrals. So don't worry about saying, well, on the other integral we did this. Doesn't mean we have to do that. These are separate problems now. So let's look at this first one here. Sine theta over cosine squared theta plus 1. Now looking at this, there's sort of one thing that jumps out is that it says, we have that sine theta upstairs, and I see a cosine downstairs, and sine and cosine are pretty much derivatives of each other. Up to a sine, they're pretty much derivatives of each other. So it says, this really looks like the sine theta d theta is setting up to be a really nice derivative of something. So what can we do? Well, you can set u to be cosine, so that our derivative would be the top. Well, almost, because derivative of cosine is not quite sine, it's negative sine. But there's a way to fix that. We just move the negative across. So minus du would become sine. So if we make that substitution, what would we get? Well, we would get the integral of minus du, that's the sine theta d theta, over u squared plus 1. And is this an integral that we know how to do? Yeah, it is. It's a lovely integral. It's on our list of 8. So this is minus arctangent of u. Now, of course, plus c. So this becomes minus arctangent of u, which is, not sine, it's cosine, plus c. Okay. All right, so we have that. Now, we come to the second integral and we say, what do we do here? Now, you are absolutely allowed to let u equal cosine, and if you do that, you will get the answer, but I just want to point out that you don't have to do that, because we have a slightly different numerator this time, and we say to ourselves, we have cosine squared theta plus 1, and you should sort of try to, in your head, say, well, what if I try different things? Well, let's try a different type of substitution here. What's a different substitution that can be made? Well, sine theta we'd have a harder time with. You could try that, but I'm thinking of, let's just make the whole denominator our substitution. Now, this seems to be aggressive, but you can always try things. And if it doesn't work, then there's a good technique called try something else. In fact, it's almost a flawless system. Try something. If it doesn't work, try something else. But never give up until the test is over. Or you have everything solved. What's the derivative of cosine squared? Think of it as the cosine being squared, so it's a function, cosine inside the square function. So chain rule. The 2 comes down, cosine to the 1, times the derivative of the cosine, which is negative sine. Again, I can move the negative across. Notice 2 sine cosine theta d theta, that's right up there. So that becomes minus du. And this cosine squared theta plus 1, that's our du. Oftentimes, when you have a fraction, especially when you have a fraction, you have addition downstairs, there's kind of 2 things you should be thinking of. One of them is like, can I make it look like arctangent? Which is what happened to the first one. Which is to say, if I make a good substitution, I get u squared plus 1 downstairs. But the other thing you should think of is, can I make it look like a log. So log looks like 1 over u. And this is a case where we can make it look like a log. And so what happens? Well, so the second one, if we include this minus out here as well, so we have minus the integral of minus du over u. Minus minus goes away. So that becomes, well, what? Well, that's on our list of 8. Log of u. But, of course, log of u is log of cosine squared theta plus 1, but I should add a constant here. Whoops. There we go. Plus cosine squared theta plus 1 plus a constant. So I put these two together. I don't need two separate constants. I can combine them together. So our final answer, minus arctangent of cosine theta plus log cosine squared theta plus 1 plus some constant. And we're done with that one. Don't worry, we're getting closer to the end. All right. Find the integral of e to the negative z secant squared of 3z plus log of 2z over 2. So, what do we do? Well, I think this is one that, so we're getting to almost our cool down phase. We're coming up to our end here. So, think of this as three integrals. E to the minus z dz, integral of secant squared 3z dz, plus integral log of 2z over z dz. Now, some of these we can do without much thought. Some of them we have to give a little bit of thought. Some of them we might have to give a lot of thought. Do we know the antiderivative of e to the negative z? Well, I hope it's e to the negative z, but then we have to compensate for that minus. So we put the minus in front. Do we know the integral of secant squared of 3z? Well, let's start. Do we know the integral of secant squared? Tangent. So it's going to be a tangent of 3z, but now you have to compensate for the 3z. So what do? Divide it by 3, or times it by a third. So the first two are pretty straightforward. What about log of 2z over z? What can we do there? Well, we could certainly break up natural, well, yeah, we can break up natural log. It's natural log of 2 plus natural log of z. But you still end up with ultimately the same problem. How do you integrate log z over z? Well, now, here we should really think of it as we kind of have two parts. We have log z and 1 over z. And whenever you see two parts, you sort of start to ask yourself the question, do I know some relationship between log z and 1 over z? And you might say, Steve, it's log 2z. It's okay. Just log of something and 1 over z. All right. What's the relationship? 1 over z is the derivative of log of z. So that says, hey, if one of the parts is the derivative of the other part, let's do a quick substitution. Let's call that u. So u equals log of 2z. What's du? Well, 1 over 2z. Is that right? Not quite. There's something missing. There's the dz. There's still something missing. Times the 2. Because I need to do the chain rule. So it turns out the derivative of log of 2z is 1 over z dz. In other words, that's my du part. So the second integral, we'll just temporarily write it as u du. And we're going to come back and figure out what u du is. Well, okay, now we're back. What's the integral of u du? U squared over 2. And I'm at the end, so I'll toss on my plus c. And so we're ready to write our final answer. So it's minus e to the minus z plus 1/3 tangent of 3z plus 1/2 u squared. Well, u is log of 2z. So log of 2z squared and plus c. And there's our answer. Don't forget, of course, the plus c. It's kind of interesting because you would think that you'd also have to have a half to compensate for the 2. But the half in front actually is because of the square. It has nothing to do with the 2. You could have put any number you wanted in here, 5, 20. You wouldn't have to have changed the constant in the front. So a little bit of misdirection maybe. I don't know. Some fun. All right. Set up, but do not evaluate an integral to find the area bounded by the parabola x equals y squared and the line x minus y equals 2. So we know that x equals y squared is a parabola because they told us. You might say, I'm not 100% sure what a parabola x equals y squared looks like. I'll draw it for you. However, I can also sense that you're going to say, but this doesn't solve my problem because I might have to do this on a test in the near future. How am I going to draw a parabola on a test? And the answer is, if we give you a question like this, we'll be nice and draw you pictures. So our goal is not to test you as your skill as an artist. Our goal is to test to see, can you understand the math? All right, so there's our parabola. We have the line x minus y equals 2. For me, I prefer to write this as y equals x minus 2, because that's how I'm used to seeing lines, which means that we have an intercept here at negative 2. Let's say this is negative 2. It's not, but we'll say it is. And we go up a slope of 1. All right. So we want to find the area. So here we go. There's our region. We're trying to find that region right there. So let's think about how we can do this. We're going to do this with integrals, and it says we're going to do it as an integral with respect to x and as an integral with respect to y. So we're going to do it in 2 different ways. So what does it mean to do it in 2 different ways? Well, okay, we're going to do it with respect to x. So when we integrate with respect to x, we need to know a couple of things. We need to know the curves. We need to know where we start and where we stop. So we should find some things. We should find some very simple points. Some of the points are easy to find. The parabola is at the point 0, 0. These points here, where the line and the parabola intersect, we can find those points by just figuring out what happens to when are these things equal. So for instance, here we're told that x equals y squared, and we're also told that y equals x minus 2. So we could say that, for instance, y equals y squared minus 2, or 0 is equal to y squared minus y minus 2, which factors, very conveniently for us, y minus 2, y plus 1, which says that this happens at y equals negative 1 and y equals positive 2. So this is at positive 2, this is at minus 1. And to find the x values, well, we know that x, let's see, where is it? Well, if we know y, I can solve for x. So if y equals x minus 2, rearranging this, this is also the same as saying x is equal to y plus 2. So that would say that this is at 1, and this is at 3. Okay, so now we've found our points. Okay, so as an integral with respect to x, what's going to happen? Well, when I'm integrating with respect to x, that means I'm taking the top minus the bottom. And I see that initially the top minus the bottom are the 2 parabolas. Or sorry, the 2 sides of the parabola. So I should think of this as I'm going between a y equals something down to a y equals something. So this parabola of x equals y squared, if we solve for y, it becomes y equals square root of x as the top half, y equals minus square root of x as the bottom half. So I'm going from plus square root of x to minus square root of x. So I'm going to keep doing that until this point. Now what happens after that point? Well, what happens after that point is I'm still going from the top part of the parabola, but now I'm going to the line. I switch behavior. So whenever I switch behavior, that says you get to switch and do a second integral. So look for any time when a bounding curve switches behavior. So if we're doing part A, we're going to have two integrals. The first integral, I say, goes from, I start at x equals 0 to the point where I switch, which is at x equals 1, so 0 to 1. Then I'm going to take the top function, square root of x, subtract the bottom function, minus square root of x, dx. Then I'm going to add to that, from where I switch behavior, 1, to the next point where either I end or I switch. Now in this case, I'm just going to go to where I end, 1 to 3. And then it's going to be the top function, square root of x, subtract the bottom function. And so now I come, what's the bottom function? It's the line y equals x minus 2. So subtract x minus 2. And that's part A. Okay. Now there's a part B, which says, do this as an integral with respect to y. So I don't need to change the picture. It's the same picture. We're finding the same area. We're just changing how we integrate. Now, if I'm integrating with respect to x, I'm really thinking of taking vertical slices. When I'm integrating with respect to y, I'm doing horizontal slices. So when we integrate with respect to y, what do we see? Well, what we see is that we consistently, 100% of the time, always have the same right curve, the line, the same left curve, the parabola, which means we just need one integral. So sometimes it's advantageous to switch because you can change how many integrals are involved. So where's our integral going to go from? Now I'm looking at the y bounds. From y is -1 to y is 2. -1 to 2. And when I'm doing the horizontal slices, it's going to be the right minus the left. It's always large minus small. So if in doubt, just think, which one is bigger? That's the one that's on the top. So the larger value, that's the right-hand side. I need to write that in terms of x equals, well, I already have, it's x equals y plus 2. So I'm going to go right, y plus 2, subtract the left-hand side, and that's x equals y squared, dy. And that's part B. And that's done. So just in these problems, if you ever have a problem like this, just say, look for where do my bounding curves change. Anytime a bounding curve changes, you got to split up your integrals. You got to do multiple integrals. But other thing is, be ready to swap. They might say, here's x equals y squared, but I also know it's y equals square root of x. Because if you're, depending upon which way you're integrating, you might need to do something slightly different. Okay, next one. Find the integral, 0 to 1, of 3x minus 2 times 1 minus x squared to the 1/4 squared dx. I like this problem. And we put this on an exam a few years ago, but they said, Steve, you gotta tone it down a little bit. And I was like, no! But that was back in the days before I had more power. So I had to negotiate and say, okay, fine, we'll do one step for them. So this is not quite what was on the exam. What was on the exam? Well, if you saw this, let's just go through our process. Is this on our list of 8 things we know how to integrate? No, it's not. Okay, so we go to our next thing, which is there any algebra we can do? And is there? And the answer is yes, because it's a square. So we square it. So this was the part that was, they got me to say, at least square it for them. So, okay, all right, fine. We square it. So 9x squared, because we squared the first term. Then we're going to double. So it's like a squared, then 2ab. We're going to have a subtract. So 2ab will give us 12x, 1 minus x squared to the 1/4. Then the last term will be plus 4, 1 minus x squared to the 1/2. Okay. So there we go. We have that integral. That's a little bit faint. Sorry about that. But all right. Now, what do? Well, the next thing to do is to say, look, if you've got integrals, really think about instead of one big integral, think about it as 3 small integrals, and let's just work through them one at a time. So in other words, look, you can say this is 9, integral 0 to 1 of x squared. Then minus 12, integral 0 to 1 of x, 1 minus x squared to the 1/4 dx. And then plus 4, integral 0 to 1 of 1 minus x squared to the 1/2 dx. All right, well, now we're here. Let's work through these integrals one by one. Is the integral of x squared on our list of things we can integrate? In other words, can we integrate it? Yeah, we can. What is the integral of x squared? 1/3 x cubed. And we evaluate from 0 to 1. Well, very conveniently for us, 9 times 1/3 is 3, and 1 cubed is 1, 0 cubed is 0, which means that we're going to end up with 3. Okay, so the first integral, we've made it safely through. We got 3. Now we go to the middle integral. Okay, so we have 12, integral 0 to 1 of x times 1 minus x squared to the 1/4. Is that on our list of things we can integrate? No, it's not. Is there any good algebra we can do to this? No, not really. Is there a substitution we can make? And the answer is yes. What substitution looks good here? The 1 minus x squared. Because we can even see it, it looks like a function in that 1/4 function. So there's always 2 places to look for substitution. Function in a function, or something that's a nice derivative. So the best is when you have both. And here, if you set u equals to 1 minus x squared, then what does du become? Well, minus 2x dx, which is the right thing, because x dx is right there. Another way to write this is minus 1/2 du is x dx. So, updating, we can say we have minus 12 times minus 1/2 times the integral of something, u to the 1/4 du. And what will our bounds be? Well, we've got to update. 0 to 1, well, plug in 0, 1 minus 0 is 1. Plug in 1, 1 minus 1 is 0. Well, that's okay. We can fix that. We'll just flip it. So 12 times 1/2 is 6. We had 2 negatives, but one of them is going to be used to fix the order of integration. 0 to 1, u to the 1/4 du. Okay, what's the integral of u to the 1/4? Well, it's u to what power? 5/4, because we're going to add 1, and then we multiply by 4/5. And we evaluate from 0 to 1, which leaves us a grand total of negative 24/5. Okay, so that's the middle one. Okay, so what are we up to? We're up to 3. Subtract 24 over 5, which is the middle part. Now we come to the last integral. How do we integrate 1 minus x squared to the 1/2? Is it on our list of things to integrate? No. Is there a good substitution? There are substitutions we can make, but if we tried 1 minus x squared, the problem is there's not an x dx floating on the outside. Now you might say, is there any way to find the antiderivative? It turns out you can next semester in the next class. So you can't really, we haven't taught you how to find this antiderivative. And at this point you're saying, this doesn't sound fair. But you should recognize what this is. 1 minus x squared to the 1/2, square root of 1 minus x squared, things have meaning. Think of the geometry. What does the square root of 1 minus x squared look like? It starts at 1, goes down, and it is, in fact, a circle, as somebody has pointed out. Well, it's not a whole circle, really. It's part of a circle. First off, what circle is it? Well, it's a circle with radius 1. How much area is in a whole circle of radius 1? Would be pi r squared, pi 1 squared. We want just a fourth of it. So that means that this integral will be 1/4 pi, because I can interpret this integral geometrically. So whenever you see the integral involving a square root of 1 minus x squared and there's nothing else there, you should say, circle. That's a circle. They're trying to get us, but we know that's a circle. So it means our last integral, our last piece, is pi. Now we can simplify this because the first term, 3, we can write that as 15 over 5 minus 24 over 5 plus pi. And then 15 minus 24 would be negative 9, so it looks like pi minus 9/5. This would be the final answer. All right, and then we're done. Look, we did like 17 problems, and it took us a lot less than 2 hours, and you only have to do 6. So plenty of time. Don't feel the need to rush. Be methodical. Think about things. And we've done a lot of the problems, and some of the problems will be like what's on the exam. Some probably won't, because you only have 6 problems. But practice. The more you practice, the easier it'll be. And that's it. Good luck.